Hello! In this video we are going to talk about systems of linear equations. We are going to review the idea of what is a system, how to calculate solutions of a linear system, and we are not going to need many things, just some calculations of real numbers. Okay, let's just start with solutions of an equation. Imagine that you are given this equation, 2x plus 2y equals 1. So this equation has not only one solution, has an infinitely many solutions, since you can just change, for example, the value of x and the value of y in different forms, okay? You can just, if you want to see these infinite solutions, you can just solve for y and give values to x, and you will have a lot of points that verify this condition. Also, okay, if you want to plot it, the idea, this is just a straight line. If you solve for y, it's piece of cake because you are going to have a straight line directly going down, because if you solve for y, 2x goes to the other side, minus 2x, the slope is negative 1. Okay, okay, then you divide by 2 and it's not slope 2, negative 2, okay, it's negative 1. But anyway, it's just a straight line going down. All the points in this straight line verifies this equation. So as you see, you will have many solutions. Another exercise, another example. What if we consider 4x squared plus 4y squared equals to 1? Okay, be careful because in here I can just divide everything by 4. So this represents a cycle, radius 1/2. Okay, because in here I will have 1 over 4, the square root of 1 over 4 is 1/2. Okay, that is what is plotted here. How many solutions do I have here? Another infinite number of solutions, because all these points in the circumference verify this condition. Okay, so these are two equations with an infinite number of solutions. What if we put it both together? Sorry. Then the representation will give you the answer. How many solutions do I have if I consider the system formed by these two equations? Only two solutions. The plot is here. If I intersect this straight line with this cycle, as you can see, there are only 2 points in which these two figures intersect. These are the two solutions that we have. So I have one equation with an infinite number of solutions, another equation with an infinite number of solutions, but if we put it together, we only have two solutions, okay? In this case, by the way, just let me show you that the points in the representation is very easy to see, but calculating is a little bit more complicated. In the representation, as you can see, the points are 0, 1/2, and 1/2, 0. It's the solutions that you obtain here, okay? Okay, so there are systems with a unique solution and others with many solutions and infinitely many solutions, and there are others that don't have any solution. We need to find out when a system has only one solution, many infinitely solutions, or no solution at all. Okay? In this case, be careful because the system was not a linearly system, because one of the equations has x squared, y squared. This is something we are not going to see here. Okay? But it was just to give you an example that putting things together can limit the number of solutions. Okay, so solving a system is going to be defined as finding all its solution or finding out that it has none. Okay, so when we refer to solving a system, we need to find all possible solutions. It doesn't matter if the solutions are only one, are infinite number of solutions, or, as is said in this sentence, finding out if the solution has no solution. Okay, in general, what is a system of m linear equation with n unknowns? Okay, it is going to look like this, where you have numbers, the coefficients in here, that multiplies the unknowns. The unknowns are x1, x2, xn. Okay? These numbers, as I told you, are called coefficients of the system. And these numbers on the other part of the equality are called independent terms of the system. Okay? They are all real numbers. Okay? a11, a12, a1n. So why I'm using this notation A11, A1n, is because we are going to move it to matrix form in no time, and it's the same coefficient we had with matrices. Okay? Sorry. Examples of systems of equations. In here, let me see. In this system, we have 3 equations. You need to count the equations. How many variables? X, Y, T, and Z. 4 unknowns. 3 equations, 4 unknowns to find out which is the values of these unknowns. In this case, we have 2 equations, 3 unknowns. In this example, we have 2 equations, 2 unknowns only. Okay? This is just examples of systems of linear equations. Okay, what is a solution of a linear equation? A solution is a set of n real numbers. Remember that we have n unknowns. If we have, let me put an example. If you have 3 unknowns, you need 3 values to obtain a solution. If you have 4 unknowns, you need 4 values to get a solution. Okay? So we need n real numbers, the same number as unknowns, of numbers that satisfies all the equations in the system. And this all is important. Okay? When we are solving a system of equations, we need that the numbers you provide as a solution verify all possible equations. Okay? If not, it's not a solution. If it fails only with one equation, then it's not a solution. You need to keep going, finding another solution. Okay, so solving a system of equations means finding all its solutions or concluding that it has no solution. Okay, but the key point is, again, solving a system, please find all possible solutions with the definition of solution given here. Okay? The general solution of a system is the set of all solutions of the system while each of the solution is a particular solution. Okay, this is better understood when you see a solution. Okay, the general solution means that imagine that you have an infinite number of solutions. So the solutions depends on a parameter. So this is the general solution, includes all possible solutions. But if you just give the parameter one specific value, then you obtain a particular solution. The difference is important, okay? Now, let me show you an example. Here you have a system, a linear system of 2 equations, 2 unknowns. If we solve the system, I'm still not saying how we are going to do that, but if you solve the system, you obtain this only solution. X equals -10, y equals -9. Do you want to check that this is a solution? Perfect. It's a good idea. Then you replace x by -10, then you replace y by -1, and check that both equalities are true in this case, okay? The idea is that if you replace x by -10 and y by -9, the first equation should give you 7, and if you replace x and y here, the solution should be 8. You can double check and you will see that this is a particular solution. Another one, this system has no solution. It doesn't make sense from the beginning. Probably in the future you are going to recognize systems that has no solution easily. Okay, it's not so easy, but like in the example, you will see that, okay, that doesn't make sense. Why doesn't it make sense? Because 2x minus 3y needs to be 7. But the same equation, 2x minus 3y, should be equal to 0. This doesn't make sense, okay? This equation cannot be 7 and 0 at the same time, so it has no solution. The other one is that one. In this case, it's easy to see that the second equation is exactly the first equation multiplied by 2. 2 times 2 is 4, 2 times 3 is 6, 2 times 7 is 14. So we have 2 equations, but one equation is exactly the same as the previous one. In this case, you are going to find an infinite number of solutions because one of the equations, it doesn't add any information. It's useless in this case. The second one is useless. The only one I need to work with is the first one. We will see how to solve this linear system. But the key point is that x can take any value and y will have this shape. Okay, so I put alpha, for example, it's just one parameter, can take any value, and y, it's this expression. You can just solve it just calling x here alpha and solving for y. You will see that you obtain that thing. Okay? But alpha can take any value. So how many solutions do we obtain here? An infinite number of solutions. Could I just take, for example, x equal to 5, then I replace 5 here and I obtain that y equals 1. I can take alpha as 1 and I obtain that y equals minus 5 over 3. So the key idea of these things is that this is the general solution, and when I add values to alpha, then I obtain particular solutions. So this is the idea between general and particular. we normally are going to ask you to calculate the general solution, okay? The one with the parameter, okay? And remember that this means if depends on a parameter and the parameter can take any value, we are obtaining an infinite number of solutions. Okay, names. If we obtain one only solution, the system is called compatible determinate. Okay, it has only one solution. If the system has no solution, we say that it's an incompatible system. And lastly, if the system has many infinite solutions, then it's compatible undeterminate system. Okay, this is just a classification of the systems in terms of the solutions they have. Okay, more things. Okay, can we move from one system to another that is easier to solve? Yes, the answer is yes, of course. Let's have this definition. The definition says the following: two systems are equivalent when they have the same solutions. Okay, if I have a system with, I don't know, one specific solution and I have another system with the same solution, then we say that these systems are equivalent. Can we transform one system into another that has the same solutions? Yes. The idea is, when we say that we are applying equivalent transformations, okay, is when we transform one system, one or more equations, into other equivalent ones. We also say that it's an equivalent transformation when solving one of the unknowns in an equation and substituting into another equations. Okay, the idea is the following, because maybe I'm not explaining myself correctly. The idea is, when we can do that, when we can transform one system, an easy way is just like in the second point, I solve one of the variables in one of the equation and I put in the other equation this unknown, okay? So I'm just solving for one variable and replacing in the other equation. Another thing that doesn't change the result is adding to one equation the result of multiplying another by a non-zero number. Okay, that is BIT, very important thing, okay? Because if I have a system of equations, I can just take one equation and add to this equation, I can add the second one multiplied by 2, for example. Then the solutions do not change, okay? And that's very important because I can just add to one equation, this equation plus another one in order to simplify the system of equations, okay? We will see this method in with much more care and with examples because it's very important. Okay, so with these transformations are used to solve systems of linear equations. Okay, so what have we seen? We have defined system of linear equations. We just introduced the idea of equivalent systems. And the most important thing you must remember is that we can transform. The idea is that we can transform one system into another with the same solutions. The idea, or what we want, is when we transform this system, we want the new system to be easier to solve. This is the key point. And in this case, in order to do that, we are going to see something that is called the Gaussian Elimination, or we are trying to obtain something that is called the row reduced echelon form. Okay, for example, we will see this in new videos. Okay, guys, thank you for your attention.